So I'm going to look forward in time to the future of nuclear energy and explore the question of what its potential role could be. We've heard about a lot of technologies already today, and a lot of it has been framed around future developments and breakthroughs. And so very much in that spirit, I'm looking to what the cutting edge of nuclear technology is now, what might happen in the next few decades and beyond that. So this is a familiar picture, the use of energy worldwide. This is primary energy. We have a range of sources, most of them fossil fuel sources, coal, natural gas and crude oil making up the majority of that pie. Nuclear is one of the larger, lesser components along with hydroelectricity. And the question here is, will that nuclear component stay the same? Many projections have it not really changing much over the next 50 years. Will it shrink as a result of accidents like Fukushima and lack of public support, or perhaps poor economic performance? Or will it in fact grow and potentially grow very significantly? This table is really just meant to illustrate 2 points. One of them, that energy use is going to grow significantly in the next 5 decades or so, which covers this projection from 2010 to 2060 based on some work I've done recently. Probably around a 3.5-fold increase in the amount of electricity demand. Electricity is going to be the key component of that energy growth, because as a final energy source, it's extremely flexible when you can use it to do many other things. And if we want to decarbonise effectively, electrification is a really important pathway for that. The other important point is that electricity itself, although only a small part currently of our total energy use, around 20 to 30% in most countries, could end up being almost all of it, because it can be used to do other things such as create synthetic fuels, run battery electric vehicles, as we've seen in other talks, a range of services that are currently provided by fuels such as oil. If we're going to do that, however, that's where the huge extra demand in electricity will come from. Now, this is a projection for Australia done by CSIRO and the group that involved Tom Hatton and his, in the first talk in this session. Now, this is a scenario that's not typically shown, but is generated by the eFuture model when you flick a switch on the model and say turn on the option to have nuclear energy. And this is really based on technological maturity and projected costs of electricity of current generation nuclear. Now, the purple section is nuclear growth. If you flick that switch, first reactors at around 2025, around half of our total electricity demand by 2050. So that modelling for Australia, tailored for Australia, done in the last year, says nuclear is a viable option if we allow it. What's the role for nuclear energy in the future energy mix in Australia and worldwide? It has a lot of potential, as that comic illustrates. Incredibly dense form of energy, millions of times more energy per unit volume than the chemical energy we can derive from fossil fuels if we can harness it. There are 2 types of nuclear reactions that we ought to consider: nuclear fission, which is the traditional type of nuclear reaction that we've managed to harness here on Earth, and in nuclear fusion, which is what goes on in the heart of the sun. This is a schematic of a typical ultra-modern nuclear reactor, the AP1000 reactor. So of the 28 reactors being built in China that Ziggy mentioned, 4 of them are the first 4 commercial AP1000 reactors. Very large, what's called a light water reactor, so uses traditional oxide fuel, enriched uranium fuel. It has a huge number of safety features that the reactors at Fukushima didn't have, including a number of passive cooling systems that would have allowed it to ride through a period of complete station blackout for around a week rather than around an hour. So there's certainly big benefits in terms of that, and the cost of building them in China is hoped to come down to quite significantly low levels through learning by doing and scaling up the number of reactors we built. But that's not really the topic of my conversation today. What I'm really focused on is Generation 4 nuclear energy and beyond, which isn't at the commercial stage right now, but some of the technologies are at a stage where they're about ready to be commercially demonstrated. Other ones are further back in that pipeline. And there are a number of other low carbon technologies mapped there. So generation 3+ nuclear, the most advanced current reactors today that are commercial are what you could order and buy essentially off the shelf and know what you were getting. Generation 4 is what you could order in the next 10 to 30 years. So we're looking in terms of the generations of nuclear energy right up here to these revolutionary designs, as they're called, whereas the previous generations were essentially an evolution of the very first commercial nuclear reactor built in the 1950s, just incremental changes. Revolutionary designs essentially throw out the rule book and start again. And the great appeal of these Generation 4 reactors is that they really do set out to solve virtually completely the 4 big barriers that Ziggy talked about to nuclear energy: the potentially poor economics, the concerns about civil safety, what to do with the nuclear waste, and how to manage the proliferation risk. Now, this reactor is not a Generation 4 reactor. It's a schematic for a Generation 3++ reactor. So it's sort of the bridge generation between the current most advanced light water reactors and Generation 4. This is called a small modular nuclear reactor. There's a pair of them here, built below grade, so underground. You could see if you look at between the 2 reactors at the top compartment, there's a semi-trailer truck there, so that gives you an idea of the scale. These are actually considered small reactors. But in terms of energy density, they are actually relatively small. The reactors each producing around 180 megawatts of power. Now, there are a number of inherent features in these that are potentially very attractive. They're small enough that you can build them in a factory, almost all of the components, and so site-based assembly is relatively rapid. And they can, because they're small, they can incorporate a number of passive safety features that means in the event of a catastrophic failure, say, of external power, some disaster, not only are they built below grade to protect themselves, but they're completely self-protecting in the way they can passively cool, essentially forever. However, they suffer from a number of the disadvantages that current day reactors suffer from today, such as not a particularly good utilisation of the potential energy in uranium. So this is a breakdown of the major constituents of used light water reactor fuel when it comes out of a reactor after a cycle of about 18 months. What went in was essentially pure uranium, a mixture of isotopes. What comes out is mostly uranium, still around 94%. Around 5% of that uranium that comes out has been converted into energy and fission products, which are shattered uranium atoms, about half the size of uranium. About 1% of it is plutonium, and another 0.2% are other higher actinides. These are heavier elements than uranium that have been created, bred in the reactor, but not all of it consumed. Now, what the 4th generation of reactors offers, the fission reactors, is to consume all of that uranium, all of it, just about 99.9% of it, all of the plutonium and all of the transuranics. So all that it then remains is that fission product. So this is the annual mass flow for a typical light water reactor today. You have uranium mining in there, you have enrichment to increase the proportion of uranium-235, that's what's consumed in these reactors. You have spent fuel that comes out the back end. You have some types of reprocessing of that spent fuel, such as they do in France, where you can extract some of the plutonium, mix that up with fresh uranium and get more energy out of it. Ultimately, you save about 15% of the uranium by doing this. Then the rest of it, after that 1 or 2 cycles, goes into a deep geological repository to be managed for 10,000 to 100,000 years. So there are the 2 possibilities for getting rid of this fuel at the end. Direct disposal into a repository, or 1 cycle of extracting some plutonium to save about 15% of the fuel, and then direct disposal with no real impact on the radiotoxic toxic lifespan. So the fate of uranium as it's mined from the ground through to when it goes back into the ground in a repository is that almost all of it is unfortunately wasted. We still get an enormous amount of concentrated energy out of it, but ultimately we get less than 1% of the potential energy out of uranium because of these steps. A reactor such as this, which I'm with a group of people standing in front of it, there I am. This guy in the middle here, Charles Till, was one of the principal engineers and designers of this, and the experimental reactor and fuel cycling facility behind us there was demonstrated over a period of around 30 years at the Argonne National Laboratories. This concept is a closed fuel cycle where it uses a fast reactor, and I'll explain a little more about that soon, to breed new plutonium and create a closed fuel cycle by then recycling that repeatedly. So this is a simplification of what the reactor looks like. Instead of having water as a coolant, in today's commercial reactors it has a liquid metal as a coolant, in this case sodium. Still has a heat exchanger, and it has fuel that consists of uranium and a large amount of plutonium and other minor actinides. But otherwise it's still a heat engine, it still produces steam. But it uses fast neutrons, and fast neutrons are important because they're the ones that can breed new fuel readily. In other words, breed other fissionable material rather than just non-fissionable material such as is composed of most of uranium. Now there are a number of very special features about this type of design that was essentially demonstrated almost to completion at this reactor in the US. One of them is the use of metal fuel rather than oxide fuel, which has a number of huge safety advantages that I'll map out in a moment. It also allows you to use a completely different type of recycling process. It's very tolerant of impurities. It really lowers the proliferation risk because it doesn't produce the type of material that would be suitable for weapons, and it's very compact, so it improves the economics of recycling hugely. The biggest advantage, I think, about using this type of reactor is not only that it consumes all of the uranium fuel, so that's very good from an energy utilisation point of view, because it's using up to 150 times more energy out of uranium than you would get today, but also because it's consuming all of the long-lived actinides, what remains, the fission products, highly radioactive for a short amount of time. But then once you've managed them for a few hundred years, really they're not a problem anymore. So today's reactors or single-pass MOX recycle, you're looking at around 100 to 200,000 years before that spent fuel is as or less radioactive than natural rocks around a uranium mine. Whereas if you can fully recycle the actinides, then you're looking at around 300 years until it crosses that convenient threshold of being less radioactive than natural uranium ore, which is quite low on the radiotoxicology scale. So the type of fuel cycle for a generation 4 nuclear fission reactor is more like this, where we have a one-time processing of nuclear waste. So we take the waste that's already been generated from nuclear reactors over the past 50 years, we create new metal fuel out of that waste, and then we run that metal fuel through a next generation reactor and we burn it up to produce vast amounts of zero carbon electricity. We continually recycle, and what eventually goes into a repository is about 1/50th of the volume of the initial nuclear waste and has that greatly diminished lifespan. So one-time reprocessing of nuclear waste and then short lifespan of what remains when the new waste comes out of this reactor. So an integral fast reactor like this, the exemplar Generation 4 technology, has got around 50 years of research and development behind it now. It has a number of features that distinguish it from today's nuclear reactors. The coolant type is a liquid metal rather than water, which allows for fast neutrons, which provides for breeding capability. This allows you to extract eventually all of the energy out of the uranium. It has a metal fuel which confers incredibly significant safety features that I'm happy to talk about in questions. And it provides the ability to use pyroprocessing to recycle that fuel, which greatly reduces proliferation risks, improves enormously waste management and potentially is very economical. Now, there are other types of fourth generation fission reactors that are now being discussed more readily. One of them, which you may have heard of, is a thorium-based reactor. In this case, the liquid fluoride thorium reactor. Called that because a liquid salt composed mostly of fluoride salts is used to dissolve thorium within a fluid, and then the reactor core itself, the fuel, is a fluid fuel within a moderated reactor. And here's a schematic of it here. It also has a breeding blanket of salts containing thorium, where the thorium is converted into uranium-233 and then that can be fissioned in the reactor. This has a number of unique safety features associated with it. It's similar in its advantages to the integral fast reactor in that it can consume nuclear waste, albeit less efficiently than the IFR, but it can also breed enough fuel to keep itself going essentially forever. Thorium is also an extremely common fertile material, about 4 times more common than uranium even. It has a number of major safety features that are of potentially significant advantage. Then we have another stepping stone technology that's being discussed more readily in the last decade or so, and this is the fission-fusion hybrids. Now, why would you want to do this? So I'll get to fusion reactors in a moment, but why would you want to have a hybrid between a fission and a fusion reactor? Well, one of them is that a lot of the technology that we've developed for pure fusion reactors works already in a sense that we know how to do it. However, it takes more energy to run that fusion reactor than we get out of it. So in terms of a power source, it's not particularly useful. However, one thing that fusion does is produce a lot of stray neutrons. That's one of the potential problems to overcome because it can cause damage to the reactor walls. But that's a potentially huge advantage if you wrap that fusion reactor with a blanket of thorium salt, because those free neutrons can then be used to breed uranium from the thorium. So you create this breeder reactor out of a thorium reactor that's much more efficient than a standard thorium reactor. It's also potentially very attractive because in theory we know how to do that fusion component quite well. We know how to do the fission component, so we just put those two together and we've got a pathway to fusion reaction within a decadal timescale. Then we move on to the idea of a pure fusion plant. A lot of people's ideal for a future energy source, which is trying to harness what's the equivalent of the power of the sun in a controlled manner on Earth. We know we can do it in an uncontrolled manner. Fusion bombs are our most powerful bombs, and releasing enormous amounts of energy, but can we do it in this controlled manner? The most typical fusion design that's proposed is where we use an isotope of water, a heavy water isotope called deuterium. We use the lightest metal, lithium, to breed another heavy isotope of water called tritium. And within that reaction then, under extremely high temperatures and pressures, we fuse those hydrogen atoms together to produce energetic neutrons and heat energy that is then collected to run a steam generator to produce electricity. That's the theory. And the waste products then, there's some contamination of the power plant walls, but that's low-level contamination that is only a short-term issue to deal with, on a century scale. And we have helium ash, so maybe we can use that to float those airships that David King talked about earlier in the talk, because we'll have plenty of helium if we get this right. Now, this is a practical big science experiment right now. So ITER, the International Thermonuclear Experimental Reactor, is a multilateral big science experiment to prove a number of additional steps on the pathway to commercial fusion energy. The size of the reactor is significantly larger than anything else that's been built to date, around 500 megawatts thermal. The aim by the end of the program in the 2030s is to have a power gain of greater than 10, which means it's producing 10 times more energy than you're putting in to control the reaction. To do this, you require extremely high temperatures, much higher than even the core of the sun, because the pressures are considerably lower. So extremely high temperatures, and to do that we need to constrain it within a magnetic field, because if you have temperatures of 100 million degrees, you can imagine any materials, and we're worrying about materials issues at 1,000 degrees, 100 million degrees is another thing to deal with. So huge potential here, a big science experiment, multilateral collaboration between a number of major countries that are interested in developing this. Around a 10-year operational program is planned. The whole thing, construction and operation, around a $20 billion project. So this is big science, indeed fiscally the world's largest science experiment ever undertaken. The stakes are big because it's a potentially hugely abundant energy source alongside of next generation fission energy, but the risks are high as well. I think David King this morning said maybe a 50-50 bet on whether we'll ever get this working, at least within a 50-year time frame. My default argument would be we've got enough uranium and thorium fuel to comfortably last us for at least 50,000 years, so I would presume if we can't do fusion in a 50-year time frame, we probably can in a 50,000-year time frame. But if we can do it sooner, great. However, some people are not willing to just settle on banking all of their money on the big science projects like ITER. And there are a number of companies, most of them smaller scale startups, which are working in the order of a $10 to $100 million budget rather than a $20 billion budget. They're looking at often completely radical ideas for controlling fusion energy, and some of them are illustrated here. One of them involves this spinning mass of molten lead and lithium, which is then compressed with these pistons to repeatedly produce these shock waves. Other ones use a process called aneutronic fusion, which is not fully understood in terms of the physics, but would generate electricity directly rather than through the energetics of neutrons. Some companies that are serious about developing this include Lockheed Martin. So we're not talking about just some startups with no engineering background behind them, and they're proposing development cycles on the order of 10 years. Where they said we could have commercial breakthrough small fusion in the 2020s, which could completely bypass the timelines proposed by the ITER program. Now, I haven't got time to explore the plausibility of some of these programs, but there are enough of them going on, at least half a dozen, which have attracted enough serious entrepreneurial investment in the order of $10 to $100 billion to be worth considering. Some of them funded by the US Navy, other ones supported by NASA, Lockheed Martin and so on, and other ones supported by private entrepreneurs. We only really need one of these to come off and we've got an incredible breakthrough. And again, my position is if they don't come off, unfortunately, in the 2020s or 2030s, then we have fourth generation fission or fusion-fission hybrids which look extremely attractive too. Now this is important not just from the perspective of the techie world of nuclear energy or the idea of just providing electricity. Energy is a fundamental part of our entire economy, our entire civilization. Energy is effectively the ultimate raw material because if you have abundant, clean, cheap energy, there are so many things you could do, not only in terms of developing human society, but also in reducing our impact on the environment, because much of our impact on the environment is due to our inefficiencies in the way we produce food plants, in the way we build our cities and our transport networks and so on. That if we can have access to this super abundant and cheap energy, then potentially technological fixes to these major problems become realistic. So all of these types of proposals that are out there in the minds of futurists, but often at the bench scale already or beyond in terms of demonstration, for revolutionary technologies in terms of new transport fuels, new ways of producing agricultural production in urban areas that would require large energy and water inputs but hugely reduce our footprint on natural lands in terms of agricultural production, ways of fully recycling our municipal solid waste, recovering metals that currently go into landfills and so on. All of these and new ways of recycling water to address the massive issue of a deficit between the amount of clean water that we require and the amount that the environment can sustainably provide. These all become possible if you have that abundant, cheap energy. Many of the speakers in this forum will suggest it could come from renewables, and I would hope that we really do get a major expansion and breakthrough in the area. I suspect it will come through compact energy sources, super compact energy sources like advanced fission and fusion. Not all of these are in the 20 to 30 year time frame. Some of them could be built today, and the IFR is the one I talked most about because the integral fast reactor has a commercial prototype called the PRISM reactor, which has been blueprinted by General Electric Hitachi and indeed is being offered now to the UK government as a means of dealing with their plutonium stockpile and also generating clean electricity as a demonstrated closed fuel cycle for fourth generation nuclear electricity. So my vision for the next 50 years is to have a diverse energy source, to have major growth in renewables, but also to get serious about large-scale deployment of clean and sustainable forms of nuclear energy, which involve the transition from today's modern nuclear reactors through to advanced fission reactors and potentially advanced fusion reactors, such that a large portion of the future energy pie is not fossil fuels, it's in fact nuclear and renewables. A 15-fold increase in the amount of nuclear we have in the future compared to today could take up half of that total energy demand, which includes not only electricity, but our ability to produce synthetic fuels, essentially to do everything that our modern economy in 50 years' time would demand. Renewables, an expansion to a quarter of that would require around a 50-fold expansion. I expect that's probably a reasonable target for that to aim at too. So the vision thing for the future is to pursue a number of promising advanced fission technologies whilst deploying the very best light water reactor technologies we have today, moving towards the small modular reactors and trying to get some of the most promising next generation reactors deployed and commercially demonstrated as quickly as possible so that we have that plentiful energy. I put it up there as a book written just in the last year about the technology of the integral fast reactor. There's another book there about thorium with the emphasis on energy cheaper than coal. Because if we can get next generation nuclear, which is an extremely concentrated form of energy, to a point where it's cheaper than coal, we won't be building coal with carbon capture and storage, we won't be building coal in any significant amount because we'll have cleaner and cheaper alternatives. Take-home message is nuclear fuel is so dense that a golf ball sized lump of uranium or thorium would be enough to provide all of your lifetime energy needs, including all of the production of synthetic fuels, the production of agricultural produce in those vertical farms, everything within a golf ball of uranium for your lifespan, which is a very small footprint compared to, for instance, the impact of fossil fuels as they have today. Thank you.
Thank you very much for a very thought-provoking talk. I'm sure there are some questions.
I share your enthusiasm for potential of nuclear power, but I'm always troubled by that liquid sodium in your cooling systems. I mean, I know that they're built these days, or some of the submarines were built with liquid sodium as the coolant. It's used, and you say, oh well, you know, we just make sure there's no water gets in, but.
Okay, so the concern with the sodium, as you point out, is the water-sodium reaction. You know, it's a very volatile reaction if it occurs. It's a well-understood engineering problem in terms of the way these reactors have been developed over the last 50 years. The radioactive sodium is never anywhere near the supply of water. So the heat exchanger for the sodium is a secondary sodium circuit that occurs in a different area. So when sodium leaks have occurred in these reactors, it hasn't occurred anywhere near the reactor. And generally, because these reactor systems are running at atmospheric pressure, when a leak in a pipe occurs, in a light water reactor, they're operating at many hundreds of atmospheres of pressure. A break in the pipe and you get this flashing to steam immediately, and, you know, a major leak. If you have a crack in a pipe carrying sodium at atmospheric pressure, it tends to dribble out and form a skin and smoke a lot. But it's not a significant leak. However, there are other alternatives as well. If it turns out that there are more economic ways to do it than having double-walled piping and the types of mechanisms that have been used to date, such as supercritical CO2, then you never have a sodium-water interaction. So another speaker talked about the potential in solar thermal systems for supercritical CO2 as the coolant. That's been talked about readily for fast reactors as well as an alternative to avoid any sodium-water interactions, even in a non-radioactive circuit.
If I could add, on YouTube there are a number of videos from Russia where there are sodium leaks in some pipes, and it's incredibly uneventful. It's just a bloke just walks past the pipe, you know, it's a bit of smoke, bit of fire, and he just pushes it up, you know, puts almost like a handkerchief around it, and then he walks off and has another fag. I don't know whether it's fake, but you know, it's on YouTube, so it must be right. My son showed me that, by the way.
Tony Klein, University of Melbourne. There must have been an enormous amount of accumulated experience with submarine reactors and their safety. Do we know anything about, has there ever been a major serious brang with a submarine reactor?
Well, in fact, the first nuclear submarine did have a sodium-cooled reactor on it, the Seawolf, but that was quickly decommissioned. It wasn't considered economic compared to the new pressurised water reactors that they developed for those. So the fast reactors that have been run in submarine, the Russian Alpha-class submarines, are all lead-cooled reactors, which is another liquid metal coolant that you can use in a fast reactor. And there, you know, in terms of Soviet reactors, it's difficult to know whether they had accidents or how they controlled them. But there was never that issue of sodium-water reactions underwater in the ocean to consider, because there was only ever one sodium-cooled nuclear submarine.
Right, and last question.
My name is Boris Martinek from Victor Chan Cardiac Research Institute. With regard to fusion reactors, I remember I was a student that was back in late 70s, and I was at one institute where they were working on the fusion problem and so on, and telling me when I was asked when this problem might be solved because of 100 million degrees and these toroids and magnetic fields, he said around maybe 1999, 2000 and so. How far we are now from having these stable magnetic fields holding the fusion?
Well, they hope to get that resolved by the early 2020s in the ITER reactor. So that's essentially the next step, to take it from the current scale of tokamaks and stellarators through to a very large-scale, high-energy reactor. It is also a salutary lesson that the projections of any energy technology tend to far outstrip the reality of how it develops. I mean, there were proponents of solar PV saying that in the 1980s that within 10 years we wouldn't need to build coal-fired power stations anymore. Now solar PV's made huge leaps, but it obviously didn't do that. Which is why I think we have to pursue a number of these technologies, and why I'm a big promoter of the integral fast reactor, because it is one of those technologies that's been so heavily demonstrated over the last 30 years and has a commercial ready product to take to that next step, that I think there's great potential for fusion energy, but I don't think we need or ought to bank all of our nuclear options on that. If it comes off, then great, that's probably all we'll end up using. If it doesn't, then we have some, I think, fairly wonderful backups as an alternative.
Great. So thank you very much. Please join me in thanking the speaker and all the previous speakers.